Hey guys, welcome back to Cooker Chem Tutoring. I'm Austin and I'll be running through part 1 of problem set 17, the kinetic molecular theory of gases. Alright, so number 1, what is meant by the root mean square speed of gas particles? The root mean square speed refers to the particle that has the average kinetic energy of all the sample. And really beyond the meaning, as far as the definition of this root mean square goes, you don't need to know much beyond that. Okay, as long as you know that the root mean square refers to the speed of the particle, the one gas particle, that has the exact same kinetic energy as the average kinetic energy of the whole gas sample, then that's all you need to know. Okay, part B says, suppose you are at a track where 7 joggers are doing laps. Their speeds are in miles per hour, 5, 5, 4, 3, 7, 8, and 9 miles per hour. Calculate their average speed, then calculate their RMS speed, and use 3 sig figs. Okay, so hopefully you know how to do the average speed. That's pretty easy. You're just going to add them up, right? 5 plus 5 plus 4 plus 3 plus 7 plus 8 plus 9, right? And then divide it by however many there are, which happens to be 1, 2, 3, 4, 5, 6, 7, right? Okay, so we're going to divide them by 7. And then ultimately, we would get the average speed to be about 5.86 using 3 sig figs. Okay, so this would be the average speed. I'm just going to put average over here. Now, to do the root mean square speed, it actually tells you exactly what you need to do. So you're taking the root of the mean and squaring it. So what that means is you're taking the square root of all this, okay, but you're squaring each individual value and then dividing it by the total number of values. And the RMS speed would come out to be 6.20 if you do it correctly that way. Okay, so that's how you would do it using macro a macro example of joggers, for example. So typically you're not going to be using this type of application of this equation because we're going to be applying it to gases. And there's a very specific equation that we use for gases to determine the root mean square speed. But if you did use macro examples like joggers or cars or whatever it may be, this is how you would go about solving that. All right, number 2. Number 2 says, does pressure affect the root mean square speed of particles in a gas? Why or why not? Okay, so the important part of this equation or this question is going to know the equation of the root mean square speed. So the root mean square speed for gas particles looks like this: the square root of 3RT over m. Okay, where the 3 is just a 3 constant, and then the R is the R constant, which is in joules per mole Kelvin. Okay, remember there's 2 of them that we typically use. We're going to want to use this one, and I'll explain why here in a second. And then T is temperature in Kelvin. And then the M is actually molar mass in kilograms per mole, okay, instead of grams per mole. So let me explain why these are. So in order to get root mean square speed in terms of meters per second, we have to use the R constant that has joules in it, because if you remember back when we were doing thermodynamics, 1 joule is equal to 1 kilogram meter squared per second squared. And you may recognize this as the E is equal to mc squared equation, where energy is equal to the mass times the speed of light squared. And that's where we get this, because a joule is equal to, the mass of any particle times the speed of light squared. And then this is in kilograms, and this would be in meters per second, and you end up squaring that, and that looks like a joule. Okay, so in order to cancel out this kilogram here, or in the kilogram in the molar mass, we have to use the joule, because the other option would have been a liter atmosphere, and there's nothing we could do to cancel out the kilogram. So that's why we have to use that R constant. And then obviously leave your temperature in Kelvin so that the R constant can also cancel that out. So ultimately, this is the equation that you want. And let me just rewrite it down here. Okay, U RMS is equal to the square root of 3RT over M. Now, hopefully this becomes intuitive later, but at first you have to know that anything that's not in this equation, maybe this is too obvious, anything that's not in this equation is not going to affect the root mean square speed. So, for example, when we get later to, let's say, the volume or increasing volume, that's not going to affect, don't confuse this with the ideal gas law. That's not going to affect the root mean square speed of my gas particles, because even if I increase the volume, remember, root mean square is directly proportional. It's in direct proportion to the kinetic energy of my gas sample. Your kinetic energy of the gas sample does not change with volume. However, it does change with things like temperature, But mostly just with temperature. And then if the heaviness of your gas is different, then it's going to affect the speed, obviously. But really, your average kinetic energy is, in this case for gas samples, is really only dependent on temperature. So ultimately, does pressure affect the root mean square speed of gases in the gas particles? No, because it's really, you can really just say it's not in this equation, but also to kind of expand on that, it's not part of the ideal gas law. So it's just a different concept. So don't confuse those. Okay, part B says, how does the RMS speed of an N2 molecule in a gas sample change under the following conditions? Okay, assuming the gas behaves ideally. Now, we talked about temperature here. Temperature is in the equation, right? It's here. In fact, it's largely determining the RMS speed more than almost any of the other variables, because the RMS, the speeds of gas particles are directly proportional to the kinetic energy, and kinetic energy is directly proportional to the temperature. So if we're increasing the temperature, just looking at this equation mathematically, if we increase temperature here, yeah, RMS speed is going to increase as well. So I'm going to put increase here. Okay, if I increase the volume, volume's not part of this equation. So I'm going to put no effect. No effect. Volume's not going to affect this. It might affect things in terms of the gas sample, right, where we're talking about the ideal gas, but not the RMS. And then adding argon gas to the container while maintaining the same temperature. Same thing, right? It doesn't matter that we have another gas sample in there. Sure, it might be interacting, it might be bumping up against N2 particles, but that doesn't matter because we have the same temperature, okay? And so it's no effect, no effect. All right, part C says a sample of O2 gas is compressed by transferring it to a smaller container while keeping the temperature constant. What do you expect in the average? What change do you expect in the average kinetic energy of the molecules, the average speed of the molecules, the number of collisions that the molecules make with the container walls per unit time, and D, the pressure of the container? All right. So the average kinetic energy of molecules are only ever dependent on the temperature, right? And the temperature is being kept constant here. So I wouldn't expect that the kinetic energy of the molecules to increase or decrease. I would say it remain the same. Okay, remain the same. Now the average speed of the molecules is also directly proportional to the kinetic energy, which is proportional to the temperature. So I'm going to expect this to remain the same, right? If we look at the equation, URMS is equal to the square root of 3RT over M. Okay, if M is constant, right, we're not changing the identity of the gas. It's still O2, and the temperature is constant. R is constant, 3 is constant. The speed is not going to change, okay? It's going to be the same. All right, number C, or letter C here, the number of collisions that the molecules make with the container walls per unit time. If I have a box like this, and I put a bunch of particles in here, let's say gas particles are just roaming around here, and then remember they're moving at speeds here with vectors. We'll put some vectors in here. Okay, they're hitting the walls of the container with some sort of force, right, and some sort of speed. If I compress this gas sample, in other words, I've changed the volume, right? I'm putting into a smaller box, right? Then they're going to be hitting the walls of the container a lot more often, right? Because they're still moving with the same speed. It's just that they're hitting the walls. They're getting to the other wall faster than they were before because the distance has increased, okay? So I would expect that this would increase. Okay, last one, the pressure of the container. All right, so remember, now, don't get confused. What they're asking about now is the pressure of the container, and that does not relate to the RMS speed or the kinetic energy per se, okay? And this is where we actually include a little bit of the ideal gas law. Now, what's changed here? The only thing that's changed here is we've taken the gas sample and put it into a smaller container, right? So the volume has changed, right? And so how does volume relate to pressure in terms of the ideal gas law? Well, there's an equation where it's P1V1 is equal to P2V2, okay? And that means they're inversely related. So if one increases, the other decreases, right? So if I have decreased volume, right? V2 is now smaller than V1. Let's just give P1 and V1 generic numbers of 1, right? We're just assuming that whatever they had, the change in that is what matters. So P2 and V2 are what matters. So if I decrease volume, right, I have to increase pressure in order to still get 1, right? So in this case, the pressure of the container is going to increase. Now, theoretically speaking, you could probably think of that already, right? They're not, kind of with the gas particles hitting the walls of the container more often. That's actually increasing the pressure, right? You're trying to compress things that are moving really fast, and so they're going to try to push back out, right? So kind of intuitively like that, but also mathematically using this ideal gas law, that can help us figure out how the pressure of the container was changed by this situation. All right, number 3 here says rank the gases NO, NO2, N2O4, and N2O5 in order of increasing root mean square speed at 0 degrees Celsius. Okay, so remember that the RMS equation, the URMS, or the RMS speed of a gas sample, is going to be equal to the square root of 3 RT over M, okay? Now, in this case, they're all at the same temperature, so the only thing that differentiates them is M, right? The molar masses. And hopefully you can kind of see this mathematically, but as a increased mass, right, what happens to the root mean square speed? Well, it's inversely related to the molar mass. So the higher the molar mass, the lower the RMS speed. So the heavier the gas, right, the lower the RMS speed. And hopefully that makes intuitive sense, right? The heavier the gas is, I don't expect it to move as fast, right? I don't expect, I don't know, let's use, rabbits or whatever, I would expect maybe a heavier rabbit to move slower than a lighter rabbit, right? They're a little bit quicker on their feet, the lighter ones. And so it's same idea here, right? The fatter the gas is, or the fatter the particle, right, the slower it's going to move. So in terms of increasing root mean square speed, I'm going to start with the slowest one. And just looking at this, it looks like N2O5 is going to be the heaviest, right? Just knowing that it's got the most N's and the most O's in its molecular formula. So I'm going to say N2O5 first. Okay, and then in terms of increasing speed, right, I would expect probably N2O4 next because it's got the next heaviest weight. And then after that, NO2, and then NO, right? So that would be about what you would want to put. And remember, this is only dependent on their molecular weight. So whenever they ask you to rank the gases, and the gases are at the same temperature, okay, just know that the root mean square, based on the root mean square speed, just know that it's going to be from heaviest to lightest, increasing in the RMS speed, because the heaviest is going to be move the slowest, all right? All right, part B says, below is the distribution of molecular speeds of CO2 and SO2 molecules at 25 degrees Celsius. Which curve is the profile for SO2? Which of the profiles should match that of propane, a common fuel in portable grills? Explain your reasoning. Okay, so now let's look at the axes here really quick. I think that's going to help us a lot. So the fraction of the particles is right here on the x-axis. So basically, however high this is how many particles have this particular particle speed, right? So let's say, I don't know, this is like 2 times 10 to the 5th meters per second here, right? That means however many that there are a certain number of particles here that have that speed. Okay, so that's how we should read this graph. So now looking at this graph, this is a distribution, right? There are several in this gas sample, even of the individual gases, CO2 and SO2. There are different distributions of speeds. Now, up here, we've got one gas sample that has really high speeds, and the highest speed for the other one is not as high. Now, remember, we talked about lighter gases having higher root mean square speeds. Well, they also have higher distributions of speeds. So I would expect the lighter gas to be this red line because it has gas particles that reach up to these higher speeds, right? You can also look at the root mean square speed as a variable, like a statistical variable on the distribution. Remember, if you've taken stats, you'll notice that this is the mode, right? And then somewhere in here is probably the mean and then the median, or vice versa. Well, somewhere in here as well is the root mean square speed. It's probably somewhere in between the mean and the median. So just looking at that, if I were to say this is probably right here, well, then the blue one is probably right there for the RMS speed. Now, don't get confused by that. If you can just look at the ends of the graphs, that will help you just as much as well. Okay, so now in looking at the lighter gas, I'm going to expect the lighter gas to be the red line, right? So I'm going to expect this to be CO2 because SO2, S is right below carbon sulfur is right below carbon in the periodic table, which makes it heavier, right? So I'm going to guess that that's CO2, and this is SO2. Now, you'll notice that the heavier gases have what we call a narrower distribution of speeds. Notice that it's not quite that the SO2's distribution is not quite as spread out as CO2's is, right? CO2's is a little bit more spread out between the gas particles, but the SO2, it kind of hugs up against one kind of pyramid or mountain, right? And you can kind of see that in CO2 as well, but it's not as pronounced. So a question that you may get on the test is, instead of asking you, instead of giving you the graph itself, what they may ask you is something like, which of these gases will have the narrowest distribution of speeds? And you, knowing this graph and knowing the trend for heavier gases to have narrower distributions, you will have to choose the heavier gas. Okay, so I'm just letting you know that that's probably how they'll ask you this question. You may not actually get this graph on the test, and they may ask you something like which one would have the broadest distribution or which one would have the narrowest distribution, and you would expect to know which one is heavier. Okay, so which of the profiles should match that of propane, a common fuel in portable grills? Now, the one that I feel that we should that would match with propane is going to be the one that matches relatively its molecular weight. Okay. So I'm going to expect, let's look at CO2 here. CO2's molecular weight is about 44 grams per mole, okay? And then if I do SO2, let's see, that's 32, that's 64 grams per mole, okay, for SO2 and CO2. Now, C3H8, let's look at that. That's 36 plus 8. That's about 44 grams per mole for C3H8. So I would expect the red line here, let me see, I'll just put red line, to match or the one for CO2 to match that of propane, because their weights are relatively the same, so their distribution of speeds in their gas particles should be about the same. One other thing I want to note here is that on the test, they may ask you something to the effect of, you have this distribution of gases, which one would have the higher kinetic energy? Now, here's the thing. Any gas that is at the same temperature as another gas will have the same kinetic energy as that gas. Okay, so any two gases that have the same temperature, okay, in any gas sample will have the same kinetic energy. They may have a different distribution of speeds, okay, but they will have the same kinetic energy. Okay, so CO2 in this case and SO2, they have the same kinetic energy. Okay. They have the same kinetic energy in this example because they're at the same temperature. Okay, so just be wary that on the test they may ask you something like that, and they may say, of all these gases, which one has the more kinetic energy? Well, if they're at the same temperature, then they're going to have the same kinetic energy, all right? All right, number 4. Gases A and B have molecular weights of 65.2 grams per mole and 101.2 grams per mole, respectively. What is the RMS speed of these molecules at 23 degrees Celsius? All right, so let's look at the RMS speed equation really quick. RMS is equal to the square root of 3RT over M, okay? So I'm going to do these for each individual gas. I'm going to put U of A here and then U of B here. All right, so that is equal to the square root of 3, and then R, remember the R constant is the 8.314 joules per mole degrees Celsius, Kelvin. And then we've got to put this temperature here in Kelvin. So I'm going to, if you remember how to do that, all you have to do is take Celsius, 23, and then add 273 to it, okay? And for this one, we end up getting 296 Kelvin, 296 Kelvin. All right, so that would be the temperature I plug in here. Then on the bottom here, I put this, the molecular weight of gas A, but I have to put it in kilograms. So I'm going to move the decimal over 3 places as it becomes 0.652 kilograms per mole. Now, you don't have to go through all the canceling of units. It may help you. I'll show you just in case for just this problem, but the moles cancel out here because one's on the denominator of the unit on the top and the denominator of a unit on the bottom, so they both cancel. This Kelvin is on the numerator on the top and in the denominator of another unit, so I'm going to cancel those out as well. And then remember that 1 joule is equal to 1 kilogram meters squared per second squared. So what in this joule here, we're canceling out this kilogram, and then we're going to be left with meters per squared per second squared, and we're square rooting that. And so that's how we end up getting an answer in meters per second. All right, so if you do the math right, I'm not going to be using too many sig figs for this one, but you should technically have 3 sig figs because we're dependent on this guy, and they have the same number of sig figs. So that would be about 337 meters per second, okay? That would be the RMS speed of gas A. Then for gas B, just do the exact same thing, just plug in the different values. So here I've got 8.3, whoops, 314. I've got the same temperature, right? They're both at the same temperature, so I'm going to leave them in 296 Kelvin here. And just the only thing that changes here is I'm changing this to 0.1012 kilograms per mole. And then just solve. In this case, you get about 270 meters per second. Now, intuitively, does this make sense? Knowing that the heavier gas here, gas B, which had a molecular weight of 101.2 grams per mole, would have a slower speed than gas A. Okay, intuitively, you would expect a heavier gas to still be moving slower. So just mathematically, that's how we solve for something like this. All right, part B says, suppose you have a container of gas with a molecular weight of 16.48 grams per mole. If the RMS speed is 852.4 meters per second, what is the temperature of the gas? All right, so now we're using the RMS equation. We're just solving for a different variable. So in this case, I've got URMS, remember, is equal to the square root of 3RT over M. Hopefully you have that memorized by now. Okay, now they've given us the molecular weight and they've given us the speed and they're asking us to actually solve for temperature. So algebraically, I'm actually just going to solve for temperature first so that we know what this looks like. So I'm going to square both sides, and that would give me URMS squared is equal to 3RT over M. Okay, and then I'm just going to multiply molar mass over and cancel it out on this side. So this is just algebra. If you're struggling to understand what I'm doing here, I would just go back and do their math review on the smart work, and that may help you. Okay, so and then 3R, I just canceled it out. I just divided it over onto the other side here. So then I get temperature alone on this side. Okay, then I'm just going to plug in the values. So then the molar mass, remember, is 0.01648, right? I want to make this into kilograms, so I moved the decimal over 3 places. So kilograms per mole. And then the root mean square speed is 852.4 meters per second. And that's going to be squared, okay? And then I'm going to divide this by 3R, and then the R constant, remember, is 8.314 joules per mole Kelvin. And you can cancel out the units if you would like, but ultimately, if you did that correctly, you should get about 480 Kelvin as the correct temperature, okay? All right. Number 5 says, how is the rate of effusion of a gas related to its A, molar mass, B, root mean square speed, and C, temperature? Now, don't get confused. The rate of effusion, all that means is, let's say we have a balloon, okay, a balloon, and I've got some gas particles in here. I'll just put like 5, okay? Now, these particles, given however many they are and how fast they're moving, the effusion rate is like how fast are they leaving certain points on the balloon. Now, you'll notice that usually a balloon over time will deflate, right? But it's because of effusion. Effusion has to do with gas particles leaving through a certain point. So if I have, here's a hole, right? Here, if that's a hole, it's how fast do they leave one area to go to another through an entrance, okay? And in this case, in the balloon, there are, just various entrances throughout the balloon. And the faster the particles are moving, the faster and more likely they are to hit that hole. And so the rate of effusion is actually directly proportional to the root mean square speed. Okay, so just note that the RMS speed, as the RMS increases, so does the effusion rate. So I'm just going to effusion increase, okay? So they're directly proportional to each other. If I have higher RMS speed, I expect them to leave that balloon a lot faster. Okay, now in terms of the molar mass, right, if it's directly proportional RMS speed, then I can just look at the RMS equation. So if I look at that, 3RT over M, you'll notice that this equation helps you a lot in answering kinetic molecular theory questions. So if I increase the molar mass, right, I decrease the RMS speed. And so that's an inverse relationship, right? And then same with temperature here. If I look at, not same with temperature, but looking at temperature here, if I increase temperature, I actually increase RMS speed. So whenever you increase something and the other increases, that's a direct proportion, right? That's what we saw with the RMS speed and the effusion rate, right? When one increases, so does the other one. So that's a direct relationship. With the molar mass, it's an inversely proportional relationship because as one increases, the other decreases. And then so on and so forth. So I have the answers here. Remember, molar mass, it will be inversely proportional to the rate of effusion because it's inversely proportional to the RMS, because RMS is directly proportional to the effusion rate, and temperature is also directly proportional, okay? Oh, I hope that made some sense. All right, letter B says, which of the two outcomes shown below more accurately illustrates the effusion of gases from a balloon at constant atmospheric pressure if the red spheres have a greater root mean square speed than the blue spheres? Okay, so I would expect if the red spheres have if they have the greater root mean square speed, then I would expect them to have the higher effusion rate, right? Effusion, which means I should see less red spheres in the second situation, or when after a while, then I should see blue spheres, because blue spheres are moving slower. Okay, so their effusion rate is lower. So here, if I'm beginning here and I'm deciding between situation 1 or situation 2, right, I'm going to look at the situation where it ends up where red spheres have decreased significantly more than the blue spheres have. So I'm going to say, look at 1, 2, 3, 4, 5, 6, 7, 8. So I've got 8 red here, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 blue. Okay, 13 blue. Okay, and then this in second situation over here, I've got 1, 2, 3, 4, 5, 6, 7, 8 blue. Okay, 8 blue. And then 1, 2, 3, 4, 5, 6, 7 red. Okay, 7 red. And then over here, I've got 1, 2, 3, 4 red. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 blue. Okay, so they both have an effusion rate, right? But in this case, right, going from 13 down to 8, that's a pretty significant effusion rate, because we're losing 5 when we had originally 13, whereas in this case the red was only losing 1 in that same situation. So that actually demonstrates blue as having a higher effusion rate, but that's not the situation we want. Let's see if it's demonstrated over here, right? If we started with 8 red and we went down to 4 red, that's a pretty significant drop, right? That's half. We've gone down by half. And 13 went down to 11. Okay, that's decreased, obviously, but it's not quite a significant of a decrease as the red, which accurately depicts what we're trying to show, right? We're trying to show that the red spheres have a higher effusion rate, so there should be less of them in the second situation proportionally than there should be of the quantity of blue spheres. Okay, all right. I hope that made some sense. That will finish it up for part 1 of problem set 17, and then we'll see you in part 2.